Hello there and welcome. Tonight we are exploring something that seems invisible at first, something that exists all around you even though you might never see it directly. We are talking about radioactivity, one of the most fundamental forces in nature. It is the quiet hum beneath the surface of our planet, the energy released by atoms as they transform themselves, and it has been happening since long before humans even walked the earth. Radioactivity might sound dangerous, something locked away in laboratories and marked with warning signs, but the truth is far more interesting and far more woven into the fabric of our everyday world than most people realize. You are radioactive right now. The atoms inside your body are decaying as we speak, releasing tiny amounts of energy that you will never feel or see. This is not harmful to you. It is completely natural. It has always been this way, and it will always be this way. Tonight, we are going to walk slowly through the science of radioactivity, understanding what it is, why it happens, and how atoms decide to transform themselves into something entirely new. We will begin with the simplest question and work our way deeper and deeper into the atomic world, where the real story begins. By the time we are finished, you will understand why some atoms are stable and peaceful, content to exist in the form they are in forever, while other atoms are restless, driven by internal forces to change and transform. You will understand the invisible energy that powers the earth beneath your feet, and the forces that have shaped our world since its beginning. Radioactivity is fundamentally the spontaneous emission of energy and particles from unstable atoms. When we say an atom is radioactive, we mean that the nucleus of that atom is unstable, and because of that instability, it is constantly seeking to reach a more stable state. The nucleus will shed energy in particles in order to achieve this balance. Think of it like a system that is out of equilibrium, always trying to settle into a lower energy configuration. A boulder at the top of a hill wants to roll down. A hot cup of coffee wants to cool down. A radioactive nucleus wants to reach a state of lower energy. This preference for lower energy, for stability, is a fundamental principle that governs all of physics. This process happens naturally and continuously throughout nature. It does not require any external trigger or input of energy. The atom simply does what atoms do when they are built in a way that cannot last forever. Radioactivity is the most fundamental demonstration of nature's preference for stability, for balance, for the lowest possible energy state. An unstable nucleus will release radiation, and in doing so, it transforms. It becomes a different element entirely, or a different isotope of the same element. This transformation is called radioactive decay. Sometimes this transformation is dramatic and releases a lot of energy. Sometimes it is subtle and releases just a little, but it always happens, and it always results in the creation of something new. The remarkable thing about radioactivity is that it is completely spontaneous. Scientists cannot predict when a specific atom will decay. It might happen a nanosecond from now, or it might happen a billion years from now. No force on Earth can slow it down, or speed it up. No chemical reaction can alter it. No amount of heat or pressure can change the outcome. The nucleus does not care what molecules surround it. It does not care about temperature or pressure or any external condition whatsoever. The atom simply decays according to its own internal nature, governed by quantum mechanics, those strange and beautiful laws that govern the smallest things in the universe. This is perhaps one of the strangest and most profound aspects of radioactivity. The timing of decay is truly random and unpredictable. Radioactivity exists at every scale and in every corner of nature. Some atoms decay almost instantly, releasing their energy so quickly that sophisticated instruments are needed just to detect that they existed. Others take millions or billions of years, releasing their energy so slowly that we might observe the same atom for our entire lives and never see it decay. But they all follow the same basic principle, the same law. An unstable nucleus reaches for stability by releasing energy. And in that release, the very nature of the atom changes. Something old becomes something new. To understand what makes something radioactive, we first need to look at the architecture of atoms themselves. At the heart of every atom is the nucleus, a tiny, incredibly dense region that contains most of the atom's mass, packed into a space so small that if you were to scale an atom up to the size of a football stadium, the nucleus would still be smaller than a marble sitting at the center of the field. Imagine an entire atom being as large as a building, and the nucleus would be no bigger than a grain of sand. That is how small and how dense the nucleus is. The nucleus is made up of two types of particles called nucleons. The first type is protons, which carry a positive electrical charge. The second type is neutrons, which carry no charge at all, which is why they are called neutrons. They are neutral. Around this nucleus, arranged in electron shells at various distances, are electrons, which carry a negative charge. These electrons dance in clouds around the nucleus, and the way they are arranged determines how the atom behaves chemically, how it bonds with other atoms, what color it appears, what reactions it can undergo. But for the purposes of understanding radioactivity, we can largely ignore the electrons. The story of radioactivity is fundamentally a story about the nucleus, what happens in that tiny, dense center. The number of protons in a nucleus determines what element the atom is. This is the defining characteristic of an element. Hydrogen has 1 proton, helium has 2 protons, lithium has 3, carbon has 6, oxygen has 8, iron has 26, gold has 79, uranium has 92. Add or remove a single proton, and you have a completely different element, a completely different substance with completely different properties. The number of neutrons, however, can vary. You can have carbon atoms with 6 neutrons, or carbon atoms with 7 neutrons, or carbon atoms with 8 neutrons. All of these are still carbon because they all have 6 protons, but they are different forms of carbon, and they are called different isotopes of carbon. Isotopes have the same number of protons, but different numbers of neutrons. The total of protons plus neutrons gives you the mass number, which tells you roughly how heavy the atom is. So when we talk about carbon-12, we mean carbon with 6 protons and 6 neutrons, giving it a mass number of 12. Carbon-13 would have 6 protons and 7 neutrons. Carbon-14 means carbon with 6 protons and 8 neutrons. The isotope name tells you the mass number, and knowing the element tells you the number of protons, so you can always figure out the number of neutrons. The architecture of the atom is elegant and ordered. The electrons form shells around the nucleus in predictable patterns, but it is the nucleus that contains the puzzle. Inside that tiny space, protons and neutrons are arranged in ways that either create stability or create danger. The nucleus stays together because of the nuclear force, one of the most powerful forces in the universe, though it only works at extremely short ranges. This is a remarkable feature of nature. The nuclear force is an attractive force that acts between nucleons, pulling them together with tremendous strength, binding them into a coherent nucleus. Without this force, the nucleus would fall apart almost instantly because of electrostatic repulsion. Protons, being positively charged, naturally repel each other. Remember that opposite charges attract and like charges repel. So 2 protons placed near each other would push away from each other with considerable force, unless something much stronger held them together. That something is the nuclear force. It is incredibly powerful, tremendously strong, but it only works when particles are very, very close to each other. The range of the nuclear force is incredibly tiny, just a few femtometers, a femtometer being 1/4,000,000th of a meter. Step even a tiny distance beyond this range away, and its influence drops dramatically. You could move away just a hair's breadth by atomic standards, and the force would become negligible. This creates a fundamental tension at the heart of every nucleus. On one hand, you have the strong nuclear force pulling all the nucleons together with tremendous power. On the other hand, you have the electrostatic repulsion pushing the protons apart. These two forces are in constant competition, locked in a struggle that determines the fate of every nucleus. In light elements like hydrogen and helium, this competition is easily managed. A single neutron can hold protons together. But as atoms get heavier and you pack more and more protons into the nucleus, the problem gets worse and worse. Now each proton is repelled by many other protons, all pushing outward at once. The nucleus has to pack all these protons into a tiny space, while the nuclear force, despite its power, has a harder and harder time keeping them all in place. The repulsion grows with each additional proton. For stable nuclei in the lighter elements, the ideal ratio of neutrons to protons is roughly 1:1. A nucleus with equal numbers of protons and neutrons tends to be stable. Oxygen-16, for example, has 8 protons and 8 neutrons. It is stable. But as atoms get heavier, the ratio changes. Nuclei with more heavy protons need more neutrons to stabilize them, to provide more nuclear force to counteract all that electrostatic repulsion. The ratio gradually increases as you go up the periodic table until, for the heaviest stable nuclei, it reaches about 1.5 neutrons for every proton. Bism. Earth-209 has 83 protons and 126 neutrons, a ratio of about 1.52. Beyond this point, as atoms get heavier and heavier, finding stability becomes increasingly and almost impossibly difficult. All elements beyond bismuth, element 83 on the periodic table, have nuclei that are inherently unstable. Their nuclei cannot find equilibrium. No amount of neutrons can provide enough nuclear force to overcome the electrostatic repulsion pushing all those protons apart. The repulsion is simply too strong. These atoms are radioactive. They must decay. There is no way around it. Why some atoms become unstable is ultimately a question of balance, of equilibrium. An atom is stable when the forces holding the nucleus together are in equilibrium with the forces trying to tear it apart. The nuclear force and the electrostatic repulsion are balanced. Nothing needs to change. An atom becomes radioactive when this balance is disrupted. When the scales tip, when one force overwhelms the other, there are several ways this can happen, several different pathways to instability. First, an atom might simply have too many protons. These heavy elements pack so many positively charged protons into such a small space that the electrostatic repulsion becomes overwhelming and almost impossible to contain. It keeps growing stronger and stronger as you add more protons. No amount of neutrons can contain it. No amount of nuclear force can overcome it. You reach a point where the nucleus is simply too heavy with protons to be stable. Second, an atom might have too many neutrons relative to its protons. The ratio is off. In this case, the extra neutrons do not help stabilize the nucleus. They do not provide useful nuclear force anymore. Instead, the weak nuclear force, which is different from the strong nuclear force and governs the transformation of neutrons into protons, becomes active. The nucleus needs to convert some of those extra neutrons into protons to reach a better balance, a better equilibrium. Third, an atom might have excess energy for other reasons. Perhaps the nucleus is in an excited state, like a spinning top that is wobbling slightly and desperately wants to still its motion. The nucleus needs to shed this excess energy to return to a lower energy state, a more stable and peaceful state. Fourth, an atom might be missing neutrons. Too many protons and not enough neutrons to balance them. The ratio is skewed the other way. In all these cases, the nucleus is unstable. It is in an agitated state. It has more internal energy than it needs. It is imbalanced, and it seeks to rid itself of that excess energy, to return to stability. The way atoms shed energy is through radioactive decay. The nucleus releases particles and radiation, and in the process, it transforms into something more stable. Sometimes it releases an alpha particle, which is a helium-4 nucleus. Sometimes it releases a beta particle, which is an electron. Sometimes it releases a beta particle, which is an electron. Sometimes it releases a gamma ray, which is pure energy. The specific type of decay depends on what kind of instability the nucleus has, but in all cases, the result is the same. The nucleus becomes more stable. Something else is created, and the atom is transformed. This is not a violent or chaotic process, though it might sound that way. It is governed by the laws of quantum mechanics, those beautiful and strange laws which describe how subatomic particles behave. According to quantum mechanics, the exact moment when a particular atom will decay cannot be predicted. Radioactivity is probabilistic, not deterministic. We can say that in a sample of 1 billion atoms, a certain percentage will decay in the next hour. We can calculate the probability, but we cannot look at a single atom and say with any certainty that atom will decay in the next second or the next billion years. This fundamental unpredictability is built into the fabric of nature at the quantum level. It is not because we lack information or lack sensitive enough instruments. It is inherent to nature itself. It applies to every radioactive atom without exception. No force can change this. No amount of heat or pressure can speed up decay or slow it down. You cannot influence the moment of decay. Each atom simply follows the quantum mechanical laws that govern its nucleus. The discovery of radioactivity came as a complete surprise to the scientific world, a shock to the prevailing understanding of atoms and matter. In the 1890s, the dominant view in physics was that atoms were solid, indivisible particles, the smallest units of matter. They were, in a sense, the building blocks of nature, the fundamental constituents, unchangeable and permanent. Atoms, the thinking went, were eternal. They could not be broken apart. They could not be transformed. They were simply what they were. Then, in 1896, a French physicist named Henri Becquerel was experimenting with minerals containing uranium. He was investigating whether elements could emit light and rays when exposed to sunlight, similar to how phosphorescent materials glow. Some substance, S, when exposed to sunlight, absorb the energy and then release it as light in the dark. Becquerel wondered if the same thing might happen with uranium. To test this, he left a uranium mineral sitting on top of a photographic plate wrapped in thick black paper. He intended to expose the mineral to sunlight and then develop the plate to see what kinds of rays might have penetrated the paper. This would tell him whether uranium could emit rays after being exposed to sunlight. But he was interrupted by cloudy weather that lasted several days and set the experiment aside, not in an orderly way, but scattered in his laboratory while he attended to other matters. When he returned weeks later and developed the plate, he was fully expecting to see nothing, because there had been no sunlight and tea, herefore no reason for the uranium to emit anything. He was shocked. The plate showed a clear and unmistakable image of the uranium mineral. Something was being emitted from the uranium itself, something powerful enough to expose a photographic plate, something that could penetrate thick paper and expose the emulsion in complete darkness. Whatever this radiation was, it was not coming from sunlight. The sunlight had not been present at all. It was coming from the uranium itself. Becquerel had accidentally discovered radioactivity, though he did not yet fully understand what he had found or how profound the implications would be. He suspected that the uranium was emitting rays of some kind, some invisible radiation, but the nature of these rays remained a mystery. He could see that they had effects. He could measure them, but he could not explain them. Becquerel continued his experiments, trying to understand this phenomenon. He found that the intensity of the radiation was proportional to the amount of uranium present. More uranium meant stronger radiation. Less uranium meant weaker radiation. This was a direct and predictable relationship. He also found something even more mysterious. Chemical processes did not affect the radiation. Whether the uranium was in a pure state or in a compound, mixed with other elements, the radiation remained the same strength. This was unlike light emission or heat or most other phenomena. Chemical reactions could change the color of a substance, change its properties, change its behavior, but they could not affect the radiation coming from uranium. Whatever was causing this radiation, it seemed to be a property of the uranium atom itself, something fundamental and unchanging, something that chemistry could not touch. The pioneering work of uncovering the true nature of radioactivity fell largely to Marie Curie, a remarkable physicist who would dedicate her entire life to understanding this mysterious phenomenon. When Curie read about Becquerel's findings, she became fascinated. She sensed that this was something important, something that could reshape our understanding of matter itself. She began her own experiments, using extremely sensitive instruments called electrometers to detect and measure the radiation being emitted. These instruments could detect radiation that was far too faint for most other methods to register. She tested many different minerals and elements, trying to understand which ones emitted radiation and which ones did not. Her discoveries were astonishing and unexpected. She found that thorium was also radioactive, just like uranium. But then she made an even more surprising finding. Some minerals emitted far more radiation than could be explained by their uranium or thorium content alone. If you calculated how much radiation the uranium in a sample should emit and how much the thorium should emit, the total did not add up. The actual radiation was much stronger. This led her to a bold hypothesis. There must be other radioactive elements in these minerals, elements that had not yet been discovered by science. She began to systematically separate and concentrate the radioactive components of various minerals. This was painstaking work. She would process tons of pitchblende ore, a mineral containing uranium, separating out components and testing each one for radioactivity. Through chemistry and persistence, she isolated two previously unknown elements. She named them polonium and radium. Both were far more radioactive than uranium. The polonium was radioactive, but short-lived. The radium was both powerful and long-lived. The radium was especially remarkable in its properties. It glowed in the dark with a pale green light, a gentle but eerie luminescence. It gave off heat continuously, warming to the touch even when left alone in the dark. It seemed to violate the law of conservation of energy because it was releasing energy and heat with no apparent source. You could hold it and feel it warm in your hand. But where was all this energy coming from? This question would not be answered until scientists understood the structure of the atom and the nature of nuclear energy and the conversion of mass into energy through Einstein's famous equation. Marie Curie's work was revolutionary and groundbreaking, but it came at a terrible and tragic cost. She was exposed to massive amounts of radiation throughout her entire career. The dangers of radioactivity were not yet understood, or perhaps were not yet fully appreciated. She handled radioactive materials with bare hands. She carried test tubes of radium in her pockets next to her body. She breathed in radioactive dust and particles while working. She ingested radioactive materials without knowing the harm. Over her lifetime, she suffered from anemia, the reduction of red blood cells. She suffered from cataracts in her eyes that dimmed her vision. And eventually, she developed leukemia, blood cancer, caused directly by her exposure to radiation. She died in 1934 at the age of 66. Though she should have lived much longer, she was a victim of the very discoveries that had made her famous and renowned throughout the scientific world. Even after her death, the effects of her work persisted. Her notebooks from her research are still too radioactive to handle safely, even now, nearly a century after her death. They cannot be touched with bare skin. They cannot be opened without protection. They are stored in lead-lined boxes in the Bibliothèque Nationale in Paris, visible only behind thick glass or lead shielding. To touch her notebooks is to be exposed to the same radiation that killed her. Marie Curie's legacy extends far beyond her scientific discoveries. She opened doors for women in science during an era when few women were allowed into laboratories or universities. Her determination and brilliance set an example that still resonates today, more than 80 years after her death. But her story also serves as a somber and poignant reminder that the invisible forces of nature, though fascinating and powerful, demand respect and caution. Radioactivity is not something that only exists in laboratories or in dangerous materials locked away in vaults and bunkers. It is not something that humans created or something that only occurs in the modern world. It is fundamental to our planet itself. It has always been fundamental. The Earth was formed about 4.5 billion years ago from material that had been forged in stars and distributed through space by supernovae, the violent explosions of massive stars at the end of their lives. Some of this primordial material, this ancient stellar dust and gas, contained radioactive elements that had been created in those stellar furnaces. When our solar system coalesced and the Earth formed, these radioactive elements became locked inside our planet, trapped within the rock and matter, at the core and in the mantle. The most important radioactive elements in the Earth's interior are uranium-238, uranium-235, and thorium-232. These are heavy elements. These elements have extremely long half-lives, meaning they decay very slowly. Uranium-238 has a half-life of 4.5 billion years. This means that it takes 4.5 billion years for half of the uranium-238 atoms to decay into something else. This is roughly the same as the age of the Earth itself. This means that some uranium-238 atoms that were present when the Earth formed 4.5 billion years ago are still here today, still decaying. Half of the original uranium-238 has decayed, and half remains. The slow decay of these primordial radioactive elements releases energy deep within the Earth's interior. This energy keeps the planet's core hot, incredibly hot, thousands of degrees. It drives the convection currents in the Earth's mantle, the power plate tectonics, the slow movement of the continents and ocean floor. It is the ultimate reason that volcanoes erupt and earthquakes shake the ground. Without radioactive decay heating the interior, the Earth would have cooled down long ago, becoming a cold, dead, geologically inert sphere, with no earthquakes, no volcanoes, no geological activity whatsoever. The fact that our planet is still geologically active after billions of years, still shaping itself, still creating new land and destroying old land, is largely due to radioactivity. Radioactivity is also present at the surface of the Earth and in the air around us. Uranium, thorium, and potassium-40 are found in rocks and soil all over the world. These elements are distributed throughout the Earth's crust. Radon gas, a radioactive element produced by the decay of uranium and thorium in rocks, seeps into buildings through cracks in the foundation and basement walls. It rises up through the soil and finds its way inside. In fact, radon is the largest source of natural background radiation that most people are exposed to on a daily basis. This is not something that happens only in certain regions or only to certain people. It happens everywhere. There is background radiation in the air we breathe, in the ground beneath our feet, in the food we eat, and in the buildings where we live. Humans have never lived in a world without radiation. We have always been exposed to it. We evolved in the presence of this constant exposure. Our bodies have adapted to it. Life on Earth has developed with radioactivity as a constant environmental presence. The radioactivity in the Earth's crust is not dangerous in the normal circumstances that most people experience. The atmosphere above us and the Earth's protective magnetic field shield us from the most dangerous cosmic rays coming from space. The rocks around us emit radiation, but it is spread out over vast distances and dissipates quickly through air and space. However, in certain specific locations, where radioactive elements are concentrated in unusually high amounts, the background radiation can be elevated above normal levels. There are regions where granite bedrock is rich in uranium and thorium. These are granite-rich areas, often in mountainous or highland regions. In these areas, indoor radon levels can become high enough to pose potential health risks if proper ventilation is not maintained in buildings. But for most people in most places, natural background radiation is simply a part of the environment, something to be aware of and understand, but not something to fear or dread. The journey into understanding radioactivity is a journey into the invisible heart of matter, into the nuclear realm where atoms transform and release their energy continuously. It is a journey that began with accident and curiosity, with a scientist leaving an experiment in his laboratory and returning to find something that would challenge the fundamental understanding of what matter is and how it behaves. Radioactivity showed us that atoms are not indivisible, eternal, unchanging particles, as the scientists of that era believed. They are dynamic systems, complex and interesting, some of them unstable, always in motion at the quantum level, sometimes undergoing transformations that release tremendous energy into the universe. Throughout this first part of our exploration, we have built the foundation upon which all our further understanding will rest. We have learned that radioactivity is the spontaneous emission of energy and particles from unstable atoms that seek stability. We have learned about the architecture of atoms, about the nucleus and the forces that hold it together or tear it apart. We have learned about the nuclear force and electrostatic repulsion and their eternal competition and struggle. We have learned why some atoms are stable and peaceful, while others are restless and driven to transform themselves into something new. We have learned the story of discovery, how Becquerel found it by accident, and how Marie Curie dedicated her life to understanding it, a dedication that cost her her life, but changed science forever. And we have learned that radioactivity is not something exotic or artificial or modern. It is woven into the fabric of our planet itself. It has been here since the Earth formed. It continues even now, deep beneath our feet and in the rocks around us. In the parts that follow, we will explore the different types of radioactive decay, the various ways that atoms transform and shed their excess energy. We will learn about half-lives and how we use radioactivity to measure time and date ancient artifacts. We will discover applications of radioactivity in medicine and science and industry and technology. We will explore the fascinating history of nuclear science and the role radioactivity has played in shaping the modern world. But for now, rest here in the foundation we have built. Let the concepts settle in your mind like sediment in still water. Radioactivity is the sound of atoms transforming, the hum of nuclei seeking stability, the endless restlessness of matter as it pursues the lowest possible energy state and equilibrium. It is beautiful and complex and strange and wonderful. And it is the foundation upon which the rest of our exploration is built. Now that we understand the fundamental nature of radioactivity and what makes an atom unstable, we must turn our attention to the question of how radioactivity actually happens. What exactly occurs when an unstable nucleus decides it is time to transform? There are different ways that atoms can shed their excess energy, different pathways to stability, and each one reveals something beautiful about the inner workings of matter. The universe has developed several elegant solutions to the problem of nuclear instability, and we are going to explore each one carefully. Some nuclei eject massive particles, others transform neutrons into protons. Still others simply shed pure energy. The choice of pathway depends on what kind of imbalance the nucleus has developed, and what configuration would bring it closest to stability. When atoms are heavy and unstable, when they have accumulated too many protons and the electrostatic repulsion has become overwhelming, they often resort to the process we call alpha decay. In alpha decay, a nucleus ejects a particle known as an alpha particle. This alpha particle is actually a helium-4 nucleus, one of the most tightly bound structures in all of nature. It consists of 2 protons and 2 neutrons bound together with remarkable strength, a small but substantial piece of the original nucleus being cast off like a stone thrown from a sling. The alpha particle is so stable, so firmly bound, that it holds together through the entire process of emission and continues to exist as a distinct unit long after leaving the parent nucleus. When an alpha particle is emitted from a nucleus, the parent nucleus loses all of these particles at once in a single instant of transformation. The mass number drops by 4 because you have lost 2 protons and 2 neutrons. The atomic number drops by 2 because you have lost those 2 protons. This is deeply significant because losing protons means the atom becomes a different element entirely. The nuclear identity of the atom has changed. Uranium-238, which has 92 protons, becomes thorium-234 after it ejects an alpha particle, because thorium has only 90 protons. The newly created thorium nucleus is smaller than the original uranium nucleus, and usually closer to a stable configuration. The transformation can be written as an equation that shows what goes in and what comes out. Uranium-238 becomes thorium-234 plus an alpha particle. The numbers balance, the mass balances, the charge balances. This mathematical precision reflects the conservation laws that govern all of physics. The alpha particle itself is quite substantial and quite heavy relative to other forms of radiation. Because it carries a positive electrical charge, and because it is relatively large and carries significant mass, it does not travel very far through matter before it collides with other atoms and comes to a stop. Experiments show that alpha particles can be blocked by nothing more than a sheet of paper, or the dead outer layer of your own skin, which consists of cells that are already dead and provide a natural barrier. This might seem to make alpha radiation harmless in the environment, and for external exposure it largely is. But there is a crucial caveat that changes everything. If an alpha particle is emitted inside your body, if the radioactive material is inhaled in the form of dust or ingested in contaminated food or water, then the alpha particle becomes extraordinarily dangerous because it can interact directly with living tissue inside your lungs or digestive tract, or wherever the radioactive material has lodged. The damage caused by alpha particles inside the body can be severe and can lead to cancer and other diseases. But outside the body, in the external environment, where the alpha particles must travel through air before reaching you, alpha radiation is relatively easy to shield against. A simple barrier is often sufficient protection. Consider radium-226, one of the naturally occurring radioactive elements that Marie Curie discovered and worked with extensively in her pioneering experiments. When radium-226 undergoes alpha decay, it transforms into radon-222. The atomic number drops from 88 to 86, and the mass number drops from 226 to 222. The alpha particle that is ejected is the difference. 2 protons and 2 neutrons representing the loss of one complete alpha particle from the nucleus. The newly formed radon-222 is itself radioactive, though it is a gas at room temperature rather than a solid like radium. This radon gas can escape into the air, and eventually, it too will decay through its own process of radioactive transformation, beginning a long chain of decays that continues with each daughter nucleus undergoing its own transformation until a stable nucleus is finally reached. The journey from radium to stability takes many steps. Alpha decay is particularly common in the heavy elements. Those with many protons packed tightly together and struggling against the overwhelming electrostatic repulsion that develops when you have 90 or more protons, all trying to push away from each other simultaneously. It is nature's way of shedding excess protons and reducing the repulsion by breaking off large chunks of the nucleus. The loss of an alpha particle makes the parent nucleus significantly lighter and significantly less repulsive internally. The daughter nucleus is often much closer to stability as a result. But not all radioactivity involves the ejection of massive particles. Sometimes nuclei are unstable, not because they have too many protons, but because they have too many neutrons. When a nucleus has excess neutrons, it must find a way to convert some of them into protons to achieve a better balance, a more stable ratio. This is where beta decay comes in, and it represents a fundamentally different type of transformation from alpha decay. Beta decay is actually the most common form of radioactive decay occurring in nature. It happens when a neutron transforms into a proton, and in the process of that transformation, an electron is ejected from the nucleus, along with an antineutrino, a ghostly particle that interacts so weakly with matter that billions of antineutrinos from the sun pass through your body every second without you noticing anything at all. They pass through the entire Earth without colliding with anything. They pass through you without interacting with your atoms in any meaningful way. You are being bombarded by antineutrinos right now, and you will never feel them or detect them directly. In beta-minus decay, as it is formally called, the parent nucleus has too many neutrons and too few protons relative to what would be stable for its mass number. One of those neutrons essentially converts itself into a proton by emitting the electron. The process is mediated by the weak nuclear force, one of the four fundamental forces of nature, and it demonstrates something profound about the nature of matter. Neutrons and protons are not truly independent, unchangeable particles. They are interconvertible. A neutron can become a proton and vice versa. The electron that is emitted is called a beta particle in this context, and it carries away some of the energy released by the transformation. The antineutrino carries away the rest. The daughter nucleus has one more proton than the parent nucleus and one fewer neutron, bringing it closer to the stable ratio for its mass number. The electron that is ejected travels at nearly the speed of light, approaching velocities that would seem impossibly fast by human standards. This makes it far more penetrating than an alpha particle. Where alpha particles are stopped by paper or the dead outer layer of your skin, beta particles can penetrate through several millimeters of aluminum or other dense materials. They require shielding from materials like plastic or thin metal sheets to stop them effectively. They are much more of a health concern when encountered in the external environment because they can pass through skin and damage internal tissues without requiring ingestion or inhalation. A beta emitter can harm you from the outside. A beta emitter that is on your skin can cause damage as the electrons penetrate inward. The transformation in beta decay reveals something fundamental about the nucleus. It shows how protons and neutrons are not truly independent, unchangeable entities, but are interchangeable. The weak nuclear force, one of the four fundamental forces in the universe, governs these transformations. It operates on timescales much longer than those of alpha decay. Some beta emitters have half-lives measured in microseconds, while others take millions of years. The weak force is millions of times weaker than the strong nuclear force, which is why beta decay proceeds so much more slowly than alpha decay. It acts only inside the nucleus when particles are in direct contact. Beyond alpha particles and electrons, there is a third major way that unstable nuclei shed their excess energy. Sometimes a nucleus finds itself in an excited state, possessing more internal energy than it needs, but the configuration of protons and neutrons is already optimal. The nucleus does not need to eject massive particles or undergo transformations of neutrons into protons. Instead, It simply needs to release pure energy, nothing but energy, nothing but the vibrational excess that makes the nucleus unstable. This is where gamma radiation comes in, and it represents the purest form of radioactivity because it is energy itself. Gamma decay is the emission of gamma rays, which are photons of light with extraordinarily high energy. They are the most energetic photons in the entire electromagnetic spectrum, far exceeding anything else produced by ordinary materials or ordinary processes. If you think of light as waves traveling through space, gamma rays are waves with wavelengths so short that they are measured in trillionths of a millimeter. They are invisible to your eyes because your eyes can only see visible light. They are invisible to any instrument that is not specifically designed to detect them, but their effects are unmistakable. Consider the spectrum of light. Ordinary visible light has energy measured in a few electron volts. Ultraviolet light that can burn your skin has energy in tens of electron volts. X-rays used in medical imaging have energy measured in thousands of electron volts. But gamma rays produced by radioactive decay have energy measured in millions of electron volts. A typical gamma ray from cobalt-60 has energy of about 1.3 million electron volts. A single gamma ray photon can be hundreds of thousands to millions of times more energetic than a photon of visible light. This incredible energy is why gamma rays are so penetrating and dangerous. Because gamma rays are chargeless and massless, they interact very differently with matter than alpha or beta particles. They cannot be stopped by paper or aluminum. Where alpha particles are easily blocked and beta particles are slowed by thin metal sheets, gamma rays pass right through. Gamma radiation can penetrate several centimeters of lead or thick steel before being absorbed. Effective shielding against gamma rays requires lead several centimeters thick or concrete barriers more than a foot thick. This makes gamma radiation one of the most hazardous forms of ionizing radiation because it penetrates deeply into tissue and can damage cells far below the surface of the skin. The energy carried by gamma rays is sufficient to ionize atoms in living tissue, knocking electrons off atoms and creating free radicals that can damage DNA and proteins and cell membranes. Unlike alpha and beta particles that deposit energy over a short distance, gamma rays deposit energy across a broader area as they penetrate through tissue, causing damage to many cells simultaneously. Importantly, and this is a crucial difference from alpha and beta decay, gamma emission does not change the number of protons or neutrons in the nucleus. It does not transmute the element into something different. It does not change the atomic number or the mass number. Instead, it simply moves the nucleus from a higher energy state to a lower one, from an excited configuration to a ground state. It is the atomic equivalent of a spinning top that is wobbling slightly as it spins and gradually slows its wobbling motion until it spins smoothly and evenly. The nucleus sheds its excess vibrational energy as gamma rays, as pure electromagnetic radiation, and the resulting nucleus remains chemically identical to the parent. It has the same number of protons, and therefore it is the same element. It has the same mass number and is the same isotope. The only difference is that the nucleus is now in a lower, more stable energy state. It has released the excess energy that was making it unstable. One of the most important concepts in understanding radioactivity is the idea of half-life. Half-life is the amount of time required for half of the atoms in a sample to decay. It is a statistical measure that applies to large populations of atoms, but not necessarily to individual atoms. You cannot predict when a single uranium atom will decay, but you can predict that in a population of trillions of uranium atoms, after one half-life, approximately half will have decayed. If you start with 1 billion atoms of a radioactive isotope, after one half-life passes, you will have approximately 500 million atoms remaining. After two half-lives, you will have approximately 250 million remaining. After three half-lives, you will have approximately 250 million remaining. After 3 half-lives, you will have approximately 250 million remaining. After 3 half-lives, you will have approximately 125 million remaining. The decay continues in this predictable geometric fashion, with the number of atoms halving with each passing half-life. This pattern means that the activity of a sample, the rate at which it is decaying, also decreases exponentially over time. A sample that is releasing 10,000 decay events per second today will be releasing 5,000 events per second after 1 half-life, 2,500 events per second after 2 half-lives, and so on. The remarkable thing about half-life is that it is constant for any given isotope. It never changes. It is unaffected by temperature, pressure, chemical reactions, or any external condition whatsoever. You cannot speed up the decay of uranium-238 by heating it or cooling it. You cannot change its half-life by mixing it with other elements or by applying an electric field or any other force. The half-life of uranium-238 is 4.5 billion years, and it will remain 4.5 billion years for all eternity. This constancy is one of the most fundamental and useful properties of radioactivity. The half-lives of different isotopes vary enormously, spanning timescales that are almost impossible to comprehend in human terms. Some isotopes have half-lives measured in fractions of a second. These are extremely short-lived species, created only in laboratory conditions, or in the hearts of dying stars and supernovae. Krypton-101, for example, has a half-life of only about 1/10,000,000th of a second, or 100 nanoseconds. These extremely short-lived isotopes vanish almost instantaneously after they are created. They exist for only brief moments before transforming into more stable nuclei. These isotopes cannot occur naturally on Earth in any significant quantity, because they would have all decayed away long before you could measure them. They exist only in the laboratories of nuclear physicists or in the intense conditions of stellar explosions. At the other extreme, some isotopes have half-lives that are inconceivably long, longer than almost any human timescale. Thorium-232 has a half-life of 14 billion years, which is more than 3 times the current age of the Earth. This means that even after the Earth has aged considerably, even after many billions of years have passed, half of the original thorium-232 will still remain, continuing to decay at its measured pace. Uranium-238 has a half-life of 4.5 billion years, roughly comparable to the age of the Earth itself. This has profound implications. It means that since the Earth formed about 4.5 billion years ago, roughly half of the uranium-238 that was present at the beginning has decayed into other elements, while half remains. Some of that uranium-238, created in the formation of the solar system, is still here on Earth now, still decaying, still releasing energy into the Earth's interior. You are walking on top of radioactive material that has been decaying since before life first appeared on this planet. The variation in half-lives across different isotopes reveals something profound and mysterious. There is no simple pattern. 2 neighboring elements on the periodic table might have wildly different half-lives. Potassium-40, which occurs naturally in many foods and in your body right now, has a half-life of 1.3 billion years, making it relatively long-lived. But cobalt-60, used in medical applications and industrial sterilization, has a half-life of only 5.3 years. This means that cobalt-60 samples lose half their radioactivity in just over 5 years. After 10 years, they have lost 75% of their radioactivity. After 20 years, almost all of the cobalt-60 has decayed away. The specific configuration of protons and neutrons in a nucleus determines its half-life, and the possible configurations are enormously diverse. A nucleus with just a few extra neutrons might be stable or might decay with a half-life of seconds. A nucleus with just a few more extra neutrons might decay with a half-life of years or centuries. There is no predictable relationship. The details of the quantum mechanical structure of the nucleus determine what happens. This diversity is what makes radioactivity so useful scientifically. Different isotopes decay at different rates, allowing scientists to choose which isotope is best suited for a particular application. Need to image the thyroid? Use iodine-131, which has a half-life of 8 days. Need to track blood flow? Use technetium-99, which has a half-life of only 6 hours. Need to date ancient rocks? Use uranium-238, which has a half-life of billions of years. The process of radioactive decay is almost never a simple one-step transformation from one element directly to stability. Rather, when an atom decays, it often creates a daughter nucleus that is itself radioactive. This daughter nucleus will then undergo its own decay, creating a granddaughter nucleus, which might also be radioactive, leading to a great-granddaughter, and so on in a long series. This series of transformations is called a decay chain, or a decay series. The chain continues through dozens of intermediate steps until a stable nucleus is finally reached, at which point the transformations cease and the nucleus remains as it is forever. It is like a river finding its way downhill through many twists and turns until it finally reaches the ocean and flows no more. Uranium-238, for example, sits at the top of one of nature's longest and most complex decay chains. When uranium-238 undergoes alpha decay, it becomes thorium-234. Thorium-234 is radioactive and undergoes beta- decay, becoming protactinium-234. Protactinium-234 undergoes beta- decay, becoming uranium-234. Uranium-234 is itself radioactive and undergoes alpha decay, becoming thorium-232. The chain winds through thorium, protactinium, uranium, actinium, francium, radium, radon, polonium, lead, bismuth, and thallium isotopes. It takes uranium-238 through 14 distinct alpha decays and 10 beta- decays before finally reaching lead-206, which is absolutely stable and undergoes no further decay whatsoever. Once uranium-238 reaches lead-206, it is done. It will remain lead-206 for all eternity. No further transformation will occur. It has reached the bottom of the hill and will stay there forever. The entire chain from uranium-238 to lead-206 involves those 14 alpha decays and 10 beta- decays, a total of 24 steps. The time required for this entire process to occur varies tremendously depending on which isotope in the chain is the bottleneck, which decay step is so slow that it limits the overall rate. Some transformations in the chain happen in microseconds, releasing their energy so quickly that you could not possibly observe them individually. Other transformations take hours or days, but some transformations take billions of years. The rate-limiting step in the entire uranium-238 decay chain is the very first step, the alpha decay of uranium-238 itself to thorium-234, which has a half-life of 4.5 billion years. This means that the overall pace of the entire decay chain is set by this very slow first step. Even though all the subsequent steps might be much faster, the overall rate at which uranium-238 turns into lead-206 is limited by how slowly uranium-238 itself decays. The uranium-238 decay chain demonstrates a crucial principle about radioactivity. It is not an event that happens once and then is finished. It is a process that unfolds over time, sometimes over vast stretches of time that exceed the lifespan of civilizations and nations and empires. It is a process with each decay producing a new nucleus that must navigate its own pathway towards stability. The new nucleus inherits the instability left over in its structure and must find its own way to address that instability. These decay chains are found naturally throughout the Earth's crust. Uranium and thorium minerals contain samples of all the daughter products produced by these long decay chains, each at a different stage of their own decay towards stability. A piece of granite containing uranium ore contains not just uranium-238, but also thorium-234, protactinium-234, uranium-234, thorium-230, all the way down the chain. Each of these isotopes is present in a specific ratio that depends on how long the rock has been sitting there and decaying. By measuring the ratios of parent and daughter isotopes in ancient rocks, geologists can determine how long ago the rock formed. The ratio contains a record of time written in atoms. One of the most remarkable and practical applications of radioactive decay is the technique of radiocarbon dating, also known as carbon-14 dating. This technique has revolutionized archaeology and our understanding of human history and the human past. It allows scientists to determine the age of organic materials, things made from once living organisms, with a precision and accuracy that was previously completely impossible. Before carbon-14 dating was developed, archaeologists and geologists had no reliable way to determine when ancient artifacts were made or when ancient organisms lived. Now, they can measure age directly by reading the clock of radioactive decay. Carbon-14 is continuously created in the atmosphere through collisions between cosmic rays coming from outer space and nitrogen atoms in the air. These high-energy cosmic rays, traveling at nearly the speed of light, strike nitrogen-14 nuclei in the upper atmosphere. When a cosmic ray collides with a nitrogen nucleus, it can knock a proton out of the nucleus and create carbon-14 in its place. The carbon-14 atoms are then quickly oxidized to form carbon dioxide, which mixes with the rest of the atmosphere. The atmosphere becomes a well-mixed reservoir of carbon dioxide containing a steady, equilibrium concentration of carbon-14 produced by cosmic rays. Living organisms, whether plants or animals, are constantly exchanging carbon with the atmosphere. A living tree absorbs carbon dioxide from the air during photosynthesis. A living animal eats plants or other animals and incorporates the carbon from its food into its tissues. A living human breathes in air containing carbon dioxide with carbon-14 in it. The carbon becomes incorporated into your bones and tissues. During the lifetime of an organism, the ratio of carbon-14 to stable carbon-12 remains constant at approximately 1 carbon-14 atom for every trillion carbon-12 atoms. This ratio matches the ratio in the atmosphere because the organism is in equilibrium with it. The organism is continuously exchanging carbon with the atmosphere, so it remains in balance. If the atmospheric ratio changes, the organism's ratio changes to match. But when an organism dies, everything changes. From that moment forward, the organism stops exchanging carbon with the atmosphere. The carbon-14 inside its tissues cannot be replenished. No new carbon-14 enters. The old carbon-14 that is present at death begins to decay through beta- decay, transforming into nitrogen-14 with a half-life of approximately 5,700 years. This clock begins ticking at the moment of death. By measuring how much of the original carbon-14 remains in a sample of organic material, scientists can calculate how long ago the organism died. The mathematics is straightforward. If a sample of ancient wood contains 1/2 of the original carbon-14 expected to be there, it must be approximately 5,700 years old, 1 half-life. If it contains 1/4 of the original carbon-14, it must be approximately 11,400 years old, 2 half-lives. If it contains 1/8 of the original, it must be approximately 17,100 years old, 3 half-lives. The measurements can be repeated multiple times to ensure accuracy, and various corrections can be applied for variations in atmospheric carbon-14 levels over time. The Sun's activity change, S over the centuries, which affects the rate of cosmic ray production, and therefore the production rate of carbon-14. Volcanic eruptions and other events that block sunlight can also affect the amount of cosmic radiation reaching the atmosphere. Scientists have created calibration curves using tree rings and other methods to account for these variations. This technique has been used to date countless artifacts that shape our understanding of human history. Egyptian mummies have been dated using carbon-14 analysis of bone and tissue samples. Ancient documents written on papyrus have been tested. The cloth wrappings of early human burials have been analyzed. Countless archaeological artifacts of wood, bone, leather, and other organic materials have been dated. It has allowed researchers to establish timelines for human civilization that previously could only be guessed at or inferred from other evidence. The Dead Sea Scrolls, ancient manuscripts discovered in caves near the Dead Sea containing some of the oldest known biblical texts and other ancient writings, have been dated using carbon-14. The dating confirmed that these scrolls were indeed written between 2000 and 2300 years ago, during the Second Temple period of ancient Judea, making them extraordinarily valuable historical documents. Carbon-14 dating has also been used to study climate change in the distant past by measuring the age of tree rings and ice cores that are thousands of years old. By determining when these materials formed, scientists can reconstruct the atmospheric conditions of ancient times. The technique has been used to investigate the diets and lifestyles of ancient peoples by analyzing the carbon-14 content of their bones and teeth, determining when they lived, and therefore understanding their chronological place in human history. Finally, we must consider uranium and its profound role in shaping our understanding of the Earth itself and its history. Uranium is the heaviest naturally occurring element, with an atomic number of 92. Its name comes from the planet Uranus, following the tradition of naming elements after celestial bodies. It exists in several isotopes in nature, with uranium-238 being by far the most common, comprising about 99.3% of all naturally occurring uranium. Uranium-235, though much less common, comprising less than 1% of natural uranium, is the isotope capable of sustaining a nuclear chain reaction, and is therefore the isotope that is used in nuclear reactors and nuclear weapons. This 1% minority isotope has shaped much of human history in the 20th and 21st centuries. Uranium is found everywhere in the Earth's crust in small amounts. It is present in soil, in rock, in groundwater, and in the sediments at the bottom of oceans and lakes. Every handful of soil contains atoms of uranium. Every beach contains uranium compounds. It has been present since the Earth formed 4.5 billion years ago. The decay of uranium-238 and uranium-235, along with thorium-232 and potassium-40, provides a significant portion of the heat that keeps the Earth's interior hot. This geothermal energy released from radioactive decay deep within the planet, drives the convection currents in the Earth's mantle and is the ultimate cause of plate tectonics, the slow movement of continental plates across the surface. It is the reason for volcanism, the eruption of molten rock from the interior. It is the reason for earthquakes, the sudden release of energy when plates shift and move. Without the slow decay of uranium and thorium in the Earth's interior, our planet would have cooled completely billions of years ago. The interior would have solidified, the mantle would have stopped moving, and our planet would be a geologically dead world with no mountains forming, no volcanoes erupting, no earthquakes shaking the ground. Radioactivity literally powers the living geology of our world. The properties of uranium decay and the discovery of radioactivity revolutionized geology and changed the science fundamentally. Before the discovery of radioactivity in the 1890s, geologists had no reliable way to determine the actual age of rocks and fossils in absolute terms. They could establish the order in which rocks were formed by studying how they were layered on top of one another and what fossils they contained. They could say that rock layer A was older than rock layer B because A was below B, but they could not determine how many years had actually passed between the formation of one rock and another. They could not determine when the Earth itself had formed. The discovery that uranium decays at a known, constant, unchangeable rate provided the first reliable method for determining absolute ages, ages measured in years rather than relative order. By measuring the ratio of uranium-238 to its daughter product, lead-206 in a rock sample, geologists can calculate how long ago the rock solidified and cooled from a molten state. Rocks from the Earth's crust can be dated this way, revealing ages ranging from a few million years for young volcanic rocks to more than 4 billion years for some of the oldest known rocks on Earth. These ancient rocks are almost as old as the Earth itself. The moon rocks brought back by Apollo astronauts during the lunar missions were dated using uranium decay methods. The analyses found that the moon rocks were about 3.7 billion years old, among the oldest lunar material. Some moon rocks are as old as 3.8 billion years. These ages tell us that the moon was forming during the early history of the solar system. Younger rocks from the moon, brought back from different landing sites, range from about 2.5 billion to 4 billion years old, depending on which region they came from. These techniques of dating through radioactive isotopes provided the first direct evidence for the age of the Earth itself. By dating the oldest meteorites that fell to Earth from the early solar system, meteorites that formed at the same time as the solar system, scientists determined that the Earth is approximately 4.5 billion years old. This age has been confirmed and reconfirmed through multiple independent methods based on radioactive decay of various isotopes. Potassium-40, samarium, rubidium, and other radioactive elements all give the same answer when used as geological clocks. The age is consistent and reliable. The Earth is about 4.5 billion years old, and it will continue to be shaped by radioactivity for billions of years to come. Yet despite all of this extraordinary utility in understanding our planet's ancient past, radioactivity remains closest to us in a way that few people ever pause to consider. You are radioactive right now. This moment, as you sit or stand and listen to these words, your body contains radioactive atoms that are decaying, releasing their energy, undergoing transformations at this very instant. You have never been separate from radioactivity. You have never existed in a state free from the subtle hum of nuclear decay happening inside your own cells. Most of the radioactivity that courses through your body comes from just two elements, potassium-40 and carbon-14. Both of these elements are essential to life. Both are found in nearly every living thing on Earth. Both have radioactive isotopes that are present in predictable, constant amounts in all organisms. You cannot avoid them because you cannot live without these elements in the first place. Potassium is fundamental to nerve function, to muscle contraction, to the regulation of fluid balance in your cells. Every heartbeat depends on potassium moving in and out of cardiac muscle cells in precisely choreographed patterns. Every thought in your brain depends on potassium ions flowing across neural membranes, creating the electrical signals that constitute consciousness itself. You cannot remove the potassium from your body any more than you could remove the water. Potassium-40, the radioactive form, makes up a small fraction of all potassium found in nature, about 1 part in 10,000. This means that if your body contains about 100 grams of potassium right now, roughly 10 milligrams of that is the radioactive isotope potassium-40. That 10 milligrams is constantly decaying, emitting beta particles and gamma rays. Every second, hundreds of potassium-40 nuclei in your body are transforming into calcium-40. It happens without your awareness, without causing any sensation, without any noticeable effect. The amount is so small that the radiation dose is entirely harmless, but it is happening nonetheless. Common foods are rich in potassium. Bananas contain so much potassium that they are often cited as the classic example of radioactive food. A single banana contains enough potassium-40 that you could theoretically detect its radioactivity with sensitive instruments. Red meats, white potatoes, carrots, lima beans, Brazil nuts, all are sources of dietary potassium. In ancient times and in modern times, people have eaten these foods and consequently carried this radioactivity in their bodies without ever knowing it. You are more radioactive after eating a banana than you were before. The increase in radiation is measurable and real, yet the effect on your health is absolutely nothing. Your body processes potassium continuously, absorbing it from food and excreting the excess through urine. The radioactive potassium-40 is processed identically to the stable isotopes. Your body cannot distinguish between potassium-40 and potassium-39. They behave chemically identically. They accumulate in your bones and muscles in the same proportions. The radioactivity is simply an invisible passenger, traveling along with an element you need to survive. Carbon-14 is equally unavoidable. Carbon forms the backbone of all organic chemistry. It is the element upon which all life depends. Your body is roughly 18% carbon by mass. Every protein, every lipid, every carbohydrate, every nucleic acid in your body contains carbon atoms. A tiny fraction of these carbon atoms are the radioactive isotope carbon-14. This isotope exists in nature because cosmic rays continuously create it in the atmosphere, and plants incorporate it through photosynthesis, and then animals eat the plants and the carbon-14 moves through food chains. You consume carbon-14 every time you eat food. You exhale carbon dioxide containing carbon-14 every time you breathe. The ratio of carbon-14 to stable carbon-12 in your body matches the ratio in the atmosphere because you are in constant exchange with it. Right now, carbon-14 nuclei in your body are decaying. They are transforming into nitrogen-14 through beta- decay. This process happens in your bones, your muscles, your organs, your brain. Thousands of carbon-14 decay events occur in your body every single second. You will never notice them. They cause no pain, no sensation, no effect. Yet they are undeniably real. There are other radioactive elements in your body as well. Polonium-210 accumulates in certain tissues. Lead-210 and radium-226 and uranium-238 are present in trace amounts. They enter through food and water and air and settle in various tissues depending on their chemical properties. The total radioactivity of the human body from all natural sources is substantial enough to measure. Scientists have conducted experiments where they place human bodies in shielded chambers and measure the gamma rays being emitted. The results confirm that humans are fundamentally radioactive organisms. An average adult human body emits roughly 8,000 decay events per second from naturally occurring radioactive elements. 8,000 times per second, nuclei in your body are undergoing decay, emitting radiation, transforming into different elements. Over the course of a lifetime, this adds up to an enormous total number of decay events. Yet because the dose is distributed across your entire body and spread across time, it causes no harm. You are adapted to live with this constant, gentle bombardment of radiation from your own atoms. Your cells have been managing this radiation exposure for billions of years, since life first emerged from the ocean onto land. You have inherited the capacity to survive in a radioactive world because your ancestors survived in a radioactive world. Now we must turn to one particular radioactive element that has shaped human history and health in ways both obvious and subtle. Radon is a colorless, odorless, tasteless gas that emerges from the ground beneath your feet. It exists because uranium and thorium in rocks decay through long decay chains that eventually produce radon-222 and radon-220. Radon atoms escape from rock and soil and begin to drift upward. Some radon reaches the surface and dissipates into the atmosphere, becoming part of the air you breathe, though in very dilute concentrations. But radon also accumulates in enclosed spaces. It seeps into basements. It enters crawl spaces and attics. It accumulates in caves and mines where rocks are exposed and people spend time underground. In these confined spaces, radon can reach concentrations high enough to become a genuine health concern. Radon-222 has a half-life of only about 4 days, but in that time it undergoes alpha decay and produces a series of short-lived daughter products. These daughters are solids rather than gases. They stick to dust particles and to the surfaces of lungs. If they are inhaled, they can lodge in lung tissue and release their radiation directly into living cells. This is where radon becomes dangerous. The risk from radon comes not from radon itself, but from its radioactive daughters. When radon decays in the lungs, it produces polonium-218 and polonium-214 and other heavy elements. These polonium isotopes are alpha emitters. They release alpha particles that have very short ranges, only a few cells deep. If the polonium is in contact with lung tissue, the alpha particles emitted can damage the DNA in lung cells directly. This damage can initiate the cascade of mutations that leads to cancer. Over years of exposure to radon and its daughters, the risk of developing lung cancer increases significantly. This is particularly true for smokers, who already have damaged lung tissue and altered immune responses. Radon is estimated to be the second leading cause of lung cancer after smoking, responsible for thousands of deaths per year in the United States alone. It is a risk that people generally do not think about because the gas is invisible and undetectable by human senses. You cannot see radon. You cannot smell it. You cannot taste it. Yet it might be accumulating in your basement right now, present in measurable concentrations, decaying and producing its radioactive daughters. Basements are particularly prone to radon accumulation because they are in contact with soil and rock, from which radon is being released constantly. Soil and rock at depth contain enough uranium and thorium that the production of radon is continuous. As radon atoms form in the pores of soil, they can escape into the air in those pores. A pressure difference can exist between the soil and the basement above it. If the basement pressure is slightly lower than soil pressure, which is common because of heating and air conditioning systems that alter air pressure in buildings, radon will be drawn upward into the home. The gas enters through foundation cracks, through gaps where pipes enter the building, through holes in the foundation, through any breach in the barrier between soil and basement. Once inside, the radon begins to decay. If people spend significant time in the basement, they are exposed to radon and its decay products. The longer the exposure and the higher the radon concentration, the greater the risk. This is why radon testing is recommended in homes, particularly in areas where soil radon levels are naturally high. Mitigation systems that reduce radon accumulation in basements can dramatically lower exposure. Simple systems that vent the radon from beneath the foundation and out through a pipe above the roof can reduce indoor radon levels by up to 90%. Understanding radon is a perfect example of how radioactivity, invisible and seemingly abstract, has real impacts on human health and requires practical solutions. Caves naturally concentrate radon even more than basements. Caves are large enclosed spaces in limestone or other rock, often in contact with uranium-bearing minerals. Radon produced in the surrounding rock can accumulate in the cave air. In caves where water has carved large chambers over millions of years, the volume is enormous, but ventilation can be limited. Radon concentrations in caves have been measured at levels far exceeding those typically found in homes. People who work in caves, such as tour guides or geologists conducting research, can accumulate significant radon exposure over the course of their careers. Some ancient cultures lived in caves, particularly in regions where cave dwellings offered protection and shelter. These people would have been exposed to elevated radon concentrations continuously. It is possible, though difficult to prove, that chronic radon exposure played some role in health problems experienced by early cave-dwelling populations. Uranium miners have historically experienced very high radon exposure. Mining operations expose huge quantities of uranium ore, releasing vast amounts of radon and its daughters into the air in enclosed underground spaces. Uranium miners develop lung cancers at rates far exceeding the general population. Before radon was recognized as the cause, the disease was called miner's lung and was attributed to dust inhalation. Only later did scientists understand that radon and its alpha-emitting daughters were the primary culprits. The history of uranium mining is intertwined with the discovery of radon's health effects. Cosmic rays reach Earth constantly from distant stars and from the Sun. These are extremely energetic particles, mostly protons, traveling at nearly the speed of light. When a cosmic ray enters Earth's atmosphere, it collides with nitrogen and oxygen atoms high above the ground. The collision has tremendous energy. The cosmic ray is stopped, but in the process of stopping, it transfers its energy to atmospheric atoms, knocking nucleons out of their nuclei and fragmenting the atoms. These collision cascades can produce secondary particles that themselves collide with atoms, creating a shower of reactions spreading downward through the atmosphere. Among the many products created by these cosmic ray interactions are radioactive isotopes. Carbon-14 is created when a cosmic ray knocks a proton out of a nitrogen-14 nucleus, leaving behind carbon-14. This process is happening constantly, at every moment, in the upper atmosphere. The carbon-14 produced is rapidly oxidized to carbon dioxide and mixed throughout the atmosphere. The steady production of carbon-14 by cosmic rays is what makes radiocarbon dating possible in the first place. Without cosmic ray production, carbon-14 would have decayed away to nothing millions of years ago. The fact that we can measure carbon-14 in ancient materials means that cosmogenic carbon-14 has been created continuously since Earth's atmosphere formed, roughly 4 billion years ago. Tritium is another cosmogenic isotope produced by cosmic ray interactions. Tritium is a radioactive isotope of hydrogen with 1 proton and 2 neutrons. It is rare in nature, but is continuously created by cosmic rays in the atmosphere. Tritium has a half-life of about 12 years, making it useful for tracing water movement. Scientists have used tritium to study how water moves through the atmosphere and falls as precipitation and infiltrates the ground. Tritium from atmospheric nuclear weapons testing in the 1950s and 1960s was dispersed worldwide and entered groundwater. By measuring tritium concentrations in groundwater, hydrologists can determine how old the water is and how quickly it is being replenished from the surface. Water with high tritium levels was recently recharged from the atmosphere. Water with low tritium levels has been isolated in aquifers for many decades. This provides a clock for understanding groundwater hydrology. Other cosmogenic isotopes are produced as well. Beryllium-10 is created when cosmic rays interact with oxygen and nitrogen. It settles onto Earth's surface and accumulates in soils and ocean sediments. Like carbon-14, beryllium-10 can be used for dating because it is continuously produced and has a known half-life. Chlorine-36 is another cosmogenic isotope useful for dating old groundwater and studying geological processes. Neon-21 is produced in the atmosphere and gets incorporated into meteorites that fall to Earth. By measuring the concentration of neon-21 in meteorites, scientists can determine how long the meteorite has been exposed to cosmic rays in space before falling to Earth. Cosmic ray production of radioactive isotopes has therefore become a major tool for understanding everything from atmospheric circulation to groundwater hydrology to the exposure history of meteorites. What happens in the upper atmosphere, initiated by particles from outer space, has profound implications for understanding Earth's surface. The isotopes created by cosmic rays are entirely natural. They have been produced since Earth's atmosphere formed. Living organisms have evolved in the presence of cosmogenic radiation and have developed biological mechanisms to repair DNA damage caused by it. But in the 1940s, human scientists began deliberately creating radioactive isotopes that do not occur naturally. This artificial radioactivity opened entirely new possibilities for research, medicine, and industry. In nuclear reactors and particle accelerators, scientists developed the ability to bombard stable nuclei with high-energy particles. When a neutron, for example, strikes a stable nucleus, it can be captured by that nucleus. The resulting nucleus has one more neutron than before and may now be unstable. If the new nucleus is radioactive, a new artificial radioisotope has been created. This process is called neutron activation. Stable cobalt-59 can be converted to radioactive cobalt-60 by bombarding it with neutrons. Cobalt-60 does not occur naturally on Earth. It is entirely artificial, created only in nuclear reactors. Yet once created, it behaves according to all the same laws of radioactive decay as naturally occurring isotopes. It has a half-life of about 5.3 years. It emits gamma radiation. It can be used in medical applications and industrial sterilization. Technetium is another element that is entirely artificial. In the periodic table, technetium has atomic number 43. All of its isotopes are radioactive with no stable form. Technetium does not occur naturally on Earth in any significant quantity, because any primordial technetium created during the formation of the solar system has long since decayed away. Technetium exists now only because scientists create it in nuclear reactors. Technetium-99m is the most important medical isotope in the world. It is used in tens of millions of diagnostic procedures every year. The M in technetium-99m stands for metastable, meaning the nucleus is in an excited state and will decay by emitting a gamma ray to reach a lower energy state. This makes technetium-99mm ideal for imaging. The gamma rays are easily detected and localized to create images of organs and tissues. The half-life of 6 hours is long enough to allow the radiopharmaceutical to be transported from the reactor to the hospital and injected into patients, yet short enough that the patient receives a reasonable radiation dose. Technetium-99m was discovered in 1938 by scientists working with molybdenum-99. Molybdenum-99 is a beta emitter with a half-life of about 65 hours. It decays into technetium-99mm. This decay relationship allows hospitals to obtain technetium-99mm on a regular schedule. Molybdenum-99 is delivered to the hospital in a special container called a technetium generator. As the molybdenum-99 decays, it produces technetium-99mm, which can be extracted from the generator as needed. The generator can be used repeatedly for about a week until the molybdenum-99 is depleted. Scientists have learned to create isotopes with specific half-lives tailored for specific purposes. For short-term imaging, isotopes with half-lives of minutes or hours are used. These minimize radiation exposure because they decay quickly. For longer-term therapy or extended diagnostic studies, isotopes with half-lives of days or weeks might be chosen. The flexibility to create isotopes with desired properties has made atomic medicine possible. Before artificial radioisotopes became available, physicians had virtually no way to visualize organ function. They could examine the structure of organs using X-rays, but X-rays show only anatomy, not function. The introduction of radiopharmaceuticals allowed doctors to see how organs were working, how blood was flowing, whether tissues were receiving adequate oxygen and nutrients. This represented a revolutionary change in medicine. Today, thousands of different radiopharmaceuticals exist, each designed to target a specific organ or tissue type, each carrying a different radioactive isotope chosen for its decay properties and penetration characteristics. Creating these isotopes requires nuclear reactors or particle accelerators. The isotopes are manufactured by specialized facilities and shipped to hospitals around the world. This entire infrastructure exists because scientists learned to artificially create radioactivity. Nuclear reactors are perhaps the most important machines ever built for producing artificial radioactivity. A nuclear reactor is a device in which a controlled nuclear chain reaction occurs. Uranium-235, the fissile isotope, can be split when struck by a neutron. The fission releases energy and additional neutrons. These new neutrons can strike other uranium-235 nuclei and cause them to fission as well. Without control, this process would escalate exponentially into an uncontrolled explosion. In a reactor, the chain reaction is controlled using neutron-absorbing materials that can be inserted or removed to adjust the rate of reaction. The earliest nuclear reactors were built during the Manhattan Project in the 1940s, with the goal of producing plutonium-239 for nuclear weapons. But reactors were quickly recognized as having many peaceful applications. They could generate electricity by using the heat from fission to boil water and drive turbines. They could produce medical isotopes by irradiating stable elements with neutrons. They could be used for research and scientific study. Today, over 400 nuclear reactors operate worldwide, generating electricity and producing isotopes. In a reactor, stable isotopes placed in the neutron-rich environment absorb neutrons and become radioactive. The rate of neutron absorption depends on the nuclear cross-section of the isotope, a measure of how likely the isotope is to capture a neutron. Some isotopes have large cross-sections and are easily converted. Others require extended exposure to neutron flux. The reactor operator can control the neutron flux and the duration of exposure to produce isotopes with specific activities, specific radioactivity levels. This level of control allows reactors to produce isotopes optimized for particular applications. Molybdenum-98 can be irradiated with neutrons to produce molybdenum-99, which is then separated and delivered to hospitals as a source of technetium-99 IMI. Cobalt-59 can be irradiated to produce cobalt-60. Iodine-127 can be irradiated to produce iodine-131. Through controlled bombardment in reactors, hundreds of useful radioisotopes are manufactured constantly. The reactor becomes a factory for creating the tools of modern medicine. The heat generated by a reactor comes from nuclear fission. When uranium-235 splits, it releases enormous energy in the form of kinetic energy of the fission fragments and neutrons and other particles. The fission fragments slow down as they collide with surrounding atoms, and their kinetic energy is converted to heat. This heat is extracted from the reactor core using a coolant, usually water. The hot coolant transfers its heat to water in a steam generator, creating steam that drives turbines connected to electrical generators. The electricity generated flows out to power homes and industries. A single uranium-235 nucleus releases about 200 million electron volts of energy when it fissions. Compare this to a chemical reaction like the combustion of methane, which releases only a few electron volts per molecule. Nuclear reactions release millions of times more energy per unit mass than chemical reactions. This enormous energy density is what makes nuclear power so attractive as a source of electricity. A relatively small amount of fuel can generate enormous quantities of power. The isotopes produced as byproducts of fission are also useful, though they can be problematic. Fission doesn't split uranium-235 nuclei into two equal pieces. Instead, it produces a variety of fission products, with different mass numbers. Some of these fission products are useful isotopes. Iodine-131 is one of the most important medical isotopes. It is produced in large quantities in reactor fission. Iodine-131 is a beta emitter with a half-life of about 8 days. It is used to treat thyroid cancer and hyperthyroidism. The thyroid gland concentrates iodine naturally, so iodine-131 is preferentially taken up by thyroid tissue. Once in the thyroid, the beta radiation emitted by the iodine-131 destroys thyroid cells. This allows high doses of radiation to be delivered to the diseased thyroid while minimizing exposure to other tissues. Iodine-131, for medical use, is extracted from the fission products produced in reactors, separated and purified, and then delivered to hospitals. Other fission products are also useful. Xenon-133 is used for lung imaging. Molybdenum-99 is used as we described to produce technetium-99m. The fission process creates a wealth of radioactive isotopes, many of which find application in medicine or research. Now let us turn to the specific ways that radioactive isotopes save lives in medical applications. The development of nuclear medicine has transformed disease diagnosis and treatment. Over 10,000 hospitals worldwide use radiopharmaceuticals regularly. More than 2 million patients per year in the United States alone undergo nuclear medicine procedures. These are ordinary, routine medical tests and treatments that would be completely impossible without radioactivity. The principle behind nuclear medicine is elegant. A radiopharmaceutical is created by attaching a radioactive isotope to a chemical compound. The compound is chosen so that it will preferentially accumulate in a particular organ or tissue. The radioactive isotope provides a signal that allows physicians to detect where He compound has accumulated. By observing where the radiopharmaceutical goes, physicians can determine whether the organ is functioning normally or whether disease is present. This represents a window into organ function that was completely unavailable to physicians before radioactivity was discovered. Consider a cardiac imaging study. A radiopharmaceutical labeled with technetium-99m is attached to a compound that is taken up by heart muscle. The patient receives an intravenous injection of this radiopharmaceutical. The blood carries the labeled compound to the heart. The heart muscle concentrates it. Then the patient lies under a gamma camera, a detector that can sense the gamma rays emitted by the technetium-99m. As the gamma rays are emitted from the heart tissue, they are detected and localized. A computer constructs an image showing where the radioactivity is concentrated. Regions of the heart that are receiving adequate blood flow will take up the radiopharmaceutical normally and will appear bright in the image. Regions that have suffered a heart attack or ischemia, where blood flow is restricted, will take up the compound poorly and will appear as dark areas. A cardiologist examining this image can immediately see whether the patient has had a heart attack, whether there is ischemia, whether the heart is functioning well. This information guides treatment. Before nuclear medicine, cardiologists had to rely on electrocardiograms and stress tests that were far less informative. Coronary angiography required threading a catheter into blood vessels, a procedure that carries real risks. Nuclear medicine cardiac imaging is non-invasive, safe, and provides detailed functional information. It has been used to evaluate millions of patients. Cancer detection and treatment has been revolutionized by radioactivity. Some cancers concentrate specific chemicals preferentially. Thyroid cancers concentrate iodine. Certain tumors concentrate glucose more than normal tissue, because cancer cells have high metabolic demands. By labeling these chemicals with radioactive isotopes, physicians can create images that highlight where cancer is present. A positron emission tomography scan, or PET scan, uses isotopes that emit positrons. A positron is the antimatter counterpart of an electron. When a positron is emitted from a nucleus, it immediately encounters an electron in the surrounding tissue. and the two annihilate each other, producing two gamma rays emitted in opposite directions. The gamma rays are detected by a ring of detectors surrounding the patient, and computers localize the annihilation event. By detecting many such events, a three-dimensional image of the distribution of the radiopharmaceutical is constructed. If the radiopharmaceutical is labeled with fluorine-18 fluorodeoxyglucose, a glucose analog labeled with the positron-emitting isotope fluorine-18, the image will show high uptake in metabolically active tissues like cancers. This allows detection of tumors that might be too small or too early in development to be visible on other imaging studies. PET imaging has become essential in cancer staging and treatment planning. Therapeutic applications of radioactivity are equally important. Iodine-131 has been used for decades to treat thyroid cancer and hyperthyroidism. The thyroid gland concentrates iodine as part of its normal function. Thyroid cancer cells and overactive thyroid tissue concentrate iodine. By administering large doses of iodine-131, radioactive iodine is concentrated in the thyroid. The beta radiation emitted by the iodine-131 destroys thyroid cells. This allows the treatment of thyroid cancer without surgery and with minimal exposure to other tissues. Millions of patients have been treated successfully with iodine-131. The treatment is remarkably effective because the thyroid takes up the iodine so eagerly and concentrates it so efficiently that very high local doses are achieved, while the rest of the body receives minimal radiation. Patients who previously would have required surgical removal of the thyroid can now be treated with a simple oral dose of radioactive iodine administered in a hospital setting. The treatment works quietly and invisibly over the course of days and weeks as the iodine-131 destroys thyroid cells from within. Bone metastases, cancers that have spread to bone, can be treated with strontium-89 or samarium-153. These isotopes concentrate in bone, particularly in areas of abnormal bone metabolism where tumors are present. The beta radiation emitted destroys cancer cells while minimizing exposure to surrounding tissue. Patients report remarkable pain relief because the radiation not only destroys cancer cells but also interrupts the nerve signals that transmit pain from bone. The treatment can be repeated periodically as needed to maintain control of the disease. These treatments have extended life expectancy and improved quality of life for patients with advanced cancers that cannot be cured but can be managed. Radioactive seed implants for prostate cancer involve placing tiny radioactive sources directly into or near the tumor. Brachytherapy is the name for this type of treatment. The seeds emit either beta or gamma radiation that destroys cancer cells at close range. Because the radiation falls off rapidly with distance, nearby healthy tissue receives much lower doses. The seeds may be temporary or permanent depending on the isotope used and the clinical situation. Over millions of patients, these radioactive treatments have proven effective and relatively safe. They have become standard treatment options that physicians routinely offer to patients facing cancer diagnoses. Finally, we must consider how radioactive isotopes serve as tracers in research and environmental monitoring. A tracer is a substance that can be followed as it moves through a system. By labeling a substance with a radioactive isotope, scientists can track its movement and determine its fate. In biological research, tritiated water can be used to measure water content in tissues. Carbon-14 labeled amino acids can be used to trace protein synthesis. Phosphorus-32 labeled nucleotides can track DNA and RNA synthesis. These labeled compounds allow researchers to follow biochemical processes in exquisite detail. The sensitivity of radioactive detection means that researchers can use extremely small quantities of labeled material and still track their fate. This allows studies to proceed without disrupting the normal biological processes being investigated. The radioactivity serves as a whispered signal. revealing the pathways of molecules through living systems without interfering with those pathways. Experiments that would be impossible using other detection methods become feasible with radioactive tracers. In environmental science, radioactive tracers are used to study water flow, sediment transport, and contaminant migration. Tritium from atmospheric nuclear weapons testing has been used extensively to date groundwater and trace groundwater flow paths. Tritium was injected into the atmosphere during nuclear weapons testing in the 1950s and 1960s, creating a pulse of radioactivity that descended through the water cycle. Rainwater containing tritium infiltrated through soil and rock to reach aquifers. By measuring tritium concentrations in groundwater, hydrologists can determine how long ago the water infiltrated from the surface and how quickly groundwater is being renewed. Water with detectable tritium levels must have been recharged from the atmosphere within the last few decades. Water from deep aquifers with no measurable tritium has been isolated from the surface for many centuries or millennia. This nuclear signature, inadvertently created by weapons testing, has become a powerful tool for understanding water resources. Iodine-129 is a long-lived isotope produced both naturally by cosmic ray interactions and artificially in nuclear reactors. It enters the environment through reactor discharge and weapons testing. Scientists use iodine-129 to trace ocean circulation patterns. By measuring iodine-129 levels in seawater samples collected from different locations, researchers can infer how water has mixed and moved through ocean basins. The radioactive signal provides a fingerprint of water masses, revealing patterns of circulation that would otherwise remain hidden. In sediment studies, radioactive isotopes are used to measure sedimentation rates and trace sediment sources. Lead-210 and cesium-137 are used to date sediments deposited in the last century. These isotopes accumulate on the ocean floor and in sediments at rates proportional to sedimentation rates, allowing scientists to determine how quickly sediment is accumulating. This information is crucial for understanding erosion, coastal evolution, and contaminant transport in aquatic systems. The sediment layers preserve a record of human activities, environmental changes, and natural processes, all revealed through the careful measurement of radioactive isotopes buried in mud and clay. Placed into the body through minimally invasive surgery. Once in position, they deliver continuous radiation directly to the tumor. This targeted approach allows treatment to continue for weeks or months, even after the patient leaves the hospital. The seeds may eventually be surgically removed or left in place to be naturally absorbed by the body as they decay. The precision of brachytherapy demonstrates how carefully scientists have learned to harness radioactivity for healing rather than harm. But detecting and measuring radioactivity requires instruments, because radiation is fundamentally invisible to human senses. You cannot see a gamma ray passing through the air. You cannot hear an alpha particle being emitted from a nucleus. You cannot feel a beta particle speeding past your skin until it has already caused damage. Radioactivity exists in a realm beyond human perception, which is why scientists develop tools to reveal what our eyes and ears cannot detect. The most famous of these instruments is the Geiger counter, named after Hans Geiger, a German physicist who developed it in the 1920s alongside Wolfgang Müller. The Geiger counter is remarkably simple in concept, though elegant in execution. Inside the device is a metal tube filled with an inert gas, usually argon, N or neon, at low pressure. The tube has two electrodes, one positive and one negative, creating an electric field between them. When a charged particle enters the tube, it ionizes the gas, stripping electrons from atoms and creating ions. The electric field accelerates these ions, which then collide with other atoms and create more ions in a cascading process called an avalanche or Townsend avalanche. This sudden flood of ions causes a brief electrical pulse that the counter detects and amplifies. The pulse generates a clicking sound or causes a needle to jump on a scale. Each click represents one ionization event, one particle detected. The beauty of the Geiger counter is that it converts an invisible nuclear event into an audible or visible signal that humans can perceive. A steady crack, pling from a Geiger counter in the presence of a radioactive source, tells the user immediately that radiation is being emitted. The sound becomes almost hypnotic when the counter is held near a highly radioactive sample. The clicking accelerates as the radiation intensity increases, creating an auditory representation of a nuclear process that has no sound of its own. The faster the clicking, the higher the radiation level. A Geiger counter doesn't measure radiation in absolute units, though. It doesn't tell you exactly how much energy is being released. It simply indicates that radiation is present and roughly how intense that radiation is. The rate of clicks must be converted to standard units by calibration against known radioactive sources. Despite this limitation, Geiger counters have been indispensable tools for scientists, medical professionals, and safety inspectors for nearly a century. They were used extensively to detect radiation in the aftermath of nuclear accidents. Firefighters and rescue workers carried them into contaminated zones to determine where radiation levels were highest and where they could safely work. Geiger counters can respond to alpha, beta, and gamma radiation, though they are more efficient at detecting some types than others. The low-energy particles are stopped by the walls of the tube itself if they don't enter the gas chamber, so external alpha radiation may not register. But beta and gamma particles penetrate more easily and are detected readily. This means a Geiger counter is excellent at detecting betas and gammas, but less useful for measuring external alpha contamination. However, if an alpha source is inside the tube chamber, it will be detected with high efficiency. Modern Geiger counters are often much more sophisticated than the original designs. Some use different detection media like scintillation crystals, which are transparent materials that produce light when struck by radiation. Others use semiconductor detectors that count the charge produced directly by the passage of a particle. Still others measure the energy of individual particles, allowing scientists to determine not just that radiation is present, but what type and energy it carries. Proportional counters can distinguish between different types of particles based on the amount of ionization they produce. Liquid scintillation counters can measure very weak radioactivity from tritium and carbon-14. Yet the fundamental principle remains unchanged since Geiger first developed his counter. An ionizing event is amplified and converted into a signal that humans can detect and measure. The ability to turn the invisible into the audible or visible was revolutionary and remains essential to radiation safety and research. Another remarkable device for visualizing radiation is the cloud chamber, invented in the early 1900s by Charles Wilson, a Scottish physicist who won a Nobel Prize for this work. It was developed before Geiger counters even existed. A cloud chamber is a sealed container filled with a supersaturated vapor, usually alcohol vapor in modern versions, though it was originally water vapor. The container is kept at a temperature and pressure where the vapor is barely stable, poised on the edge of condensation, ready to condense into liquid at the slightest disturbance. The moisture in the air is at the absolute limit of what the air can hold. When a charged particle passes through the vapor, it ionizes the atoms it encounters, stripping electrons and creating a trail of ions. These ions act as condensation nuclei, collecting points around which water or alcohol molecules preferentially accumulate. As molecules condense onto the ions, a visible trail of tiny liquid droplets forms, tracing the actual path of the particle through the vapor. The result is utterly mesmerizing to watch, almost magical in its immediacy. You can see the actual path of invisible radiation rendered visible as a thin white line in the chamber, like capturing a ghost or making the immaterial tangible. Different types of particles leave different tracks that reveal their nature to trained observers. Alpha particles, being heavy and highly charged with their 2 protons, leave thick, straight tracks that stop relatively quickly as they slow down through the vapor and give up their energy. These tracks are short and stubby, typically ending within a few centimeters of their entry point. Beta particles, being light and singly charged electrons, leave thin, winding, delicate tracks that are much longer because they lose energy more slowly to the surrounding medium. Their paths curve slightly due to interactions with the magnetic field or the random nature of collisions. Gamma rays don't leave tracks themselves because they are not charged and don't ionize atoms directly, but the electron that a gamma ray produces when it interacts with matter will leave a track, a thin line that marks the secondary particle rather than the original gamma ray. Scientists observing cloud chambers saw for the first time the visible evidence that particles existed and that they moved through matter along definable paths. The tracks were measurable. Their properties could be analyzed. Their behavior could be studied. Cloud chambers were absolutely essential in early nuclear physics research, providing the first direct visual evidence of many particles. The positron, the antimatter counterpart of the electron with identical mass but opposite charge, was discovered in 1932 by Carl Anderson in a cloud chamber photograph. Muons, which are heavier cousins of electrons with about 200 times the electron's mass, were first identified by the distinctive tracks they left in cloud chambers operated in the high mountains where cosmic rays are abundant. The technique of bubble chambers, a later refinement using superheated liquid rather than supersaturated vapor, allowed even more precise tracking of particle paths because the ionization events create bubbles that are larger and easier to photograph. The first bubble chamber was developed by Donald Glaser in 1952, revolutionizing the study of high-energy physics. In bubble chambers, particles leave clear tracks through the liquid, and the bubble formations occur along the entire path rather than just at isolated points. Modern physics experiment. TS use far more sophisticated electronic detectors that can track particles in 3 dimensions and measure their energy and momentum with extraordinary precision. Yet the principle remains the same as it was with Wilson's original cloud chamber. You create a medium sensitive to charged particles. You let particles pass through that medium. You observe the tracks they leave behind. Each track tells a story about what particle was present, how fast it was moving, and how much energy it possessed. The cloud chamber was a revolution in visualization, making the unseen visible through elegant physics. Now, radioactivity has another property that has captivated humans for centuries beyond its scientific significance. Some radioactive materials glow. They emit visible light as a result of their radioactive decay. The phenomenon is called phosphorescence or radioluminescence, depending on the specific mechanism responsible. In the early days of radioactivity, research in the 1900s, scientists noticed that radium glowed with an eerie, otherworldly greenish light when kept in darkness. The glow came from the radium's alpha particles interacting with the surrounding material, a process called Cherenkov radiation, mixed with the phosphorescence of the material itself. The alpha particles traveling through space excite electrons in nearby atoms, pushing them to higher energy states. When these excited electrons fall back to their lower energy states, they release the excess energy by emitting light. The continuous stream of alpha particles creates a continuous glow. The glow was so impressive and so novel that radium captured the public imagination in ways few elements ever have. Radium was used decoratively in luminous watch dials, allowing people to read the time in complete darkness without any external light source. The dials were painted with a mixture of radium powder, suspended in a phosphor material, typically zinc sulfide. As the radium decayed, it released alpha particles that energized the phosphor continuously. The phosphor then emitted visible light continuously, creating a permanent glow that never faded because the radium provided fresh energy from ongoing decay. Hundreds of thousands of these luminous watch dials were manufactured and sold throughout the 20th century. The technology became standard for military watches, navigation instruments, and any device that needed to be readable in darkness. But the technology came at a terrible human cost. Women workers known as the radium girls were employed in factories painting these dials with tiny brushes. They were instructed to paint fine details on watch faces and to keep the brushes point, and precise. They would lick the brush tips with their mouths between brush strokes. With each application, they ingested trace amounts of radium. The practice was so common and so casual that no one thought twice about it. Radium was considered a miracle substance, not a danger. Over years of exposure, many of these workers, particularly those who spent years in the factories, developed bone cancer, anemia, necrosis of the jaw, and other devastating illnesses. The radium accumulated in their bones, where it continued to decay, releasing radiation directly into living tissue for the remainder of their lives. Some workers died in their 20s and 30s from cancers that struck young, healthy people without warning. This tragedy was not immediately recognized as a catastrophe. The companies that employed the radium girls denied culpability for years, but eventually the cases became undeniable. The radium girls' legal battles in the 1920s established important precedents for workers' compensation and corporate responsibility for workplace safety. The tragedy revealed the true danger of radioactivity and led to much greater safety standards in industries handling radioactive materials. The use of radium in consumer products was eventually banned as the health risks became scientifically undeniable and legally unavoidable. Yet for decades before that recognition, radium was considered a wonder substance, a miracle element that would revolutionize medicine and industry. It was added to toothpaste supposedly to whiten teeth and kill bacteria. It was added to skin, creams claiming to reduce wrinkles and improve complexion. It was added to water bottles marketed as health tonics with claims of enhancing vitality. It was added to suppositories, to cosmetics, to fertilizers. The list of radium-containing consumer products is shocking to modern sensibilities. People actually believe they should be exposed to radium, should seek out and consume radioactivity because it was so powerful and energetic, and the scientists themselves seemed to regard it with respect and admiration. The belief persisted until the mounting evidence of illness and death became impossible to ignore, until the radium girls became symbols of radioactivity's hidden dangers. Today, tritium, a radioactive isotope of hydrogen, is used in some watch dials and gun sights because it glows for decades without requiring an external power source. The tritium continuously decays, continuously emitting electrons that trigger the phosphor to glow. Tritium is much safer than radium because it is a pure beta emitter, and the electrons cannot penetrate beyond the paint itself. The biological hazard from tritium is far lower than from radium. The glow of radioactive materials has been a powerful metaphor in popular culture since the early 20th century. Glowing radioactive substances appear in science fiction novels and films as sources of superpower or horrific mutation. In comic books, radiation is treated as a source of superhuman abilities. In horror films, it is a cause of monster creation. In reality, the glow is simply the result of particles exciting electrons, a process that is physically remarkable but not inherently dangerous if the radiation source is sufficiently shielded or distant. But when that source is ingested and lodges in bones, the danger becomes invisible and deadly. Throughout history, certain radioactive materials have achieved particular fame or notoriety because of their unique properties or their role in historical events and scientific discovery. Polonium is one such element, infamous for its extreme toxicity. It was discovered by Marie Curie in 1898 during her groundbreaking research on radioactivity. The element was named after her native country, Poland, as a statement of national pride and scientific accomplishment. Polonium exists only in radioactive forms, with absolutely no stable isotopes anywhere in nature. The most common naturally occurring isotope is polonium-210. It is an alpha emitter with a half-life of about 138 days. Polonium is extraordinarily dangerous if ingested or inhaled because its alpha particles, though they cannot penetrate skin, can cause devastation to living cells if they are released directly within the body, where they encounter tissue directly. A single microgram of polonium-210, an amount utterly invisible to the naked eye and smaller than a grain of sand, contains enough activity to kill a human if internalized. The danger comes not from the penetrating power of the radiation, but from its concentration of energy in a small volume. Polonium-210 has been used as a poison in espionage and assassination because of this extreme toxicity, combined with its difficulty to detect without specialized equipment. In 2006, Alexander Litvinenko, a former Russian intelligence officer and dissident, died after being poisoned with polonium-210 that was deliberately added to his tea in a London restaurant. The polonium was traced back to Russian sources through isotopic analysis, creating an international incident and demonstrating the real-world use of radioactive assassination. The toxicity of polonium illustrates how danger from radioactivity depends not on the radiation type itself, but on the pathway by which humans are exposed. Alpha particles are the least penetrating form of radiation, easily stopped by a sheet of paper or the outer layer of dead skin cells. But polonium inside the body, where it releases its alpha particles directly into living tissue and organs, is lethally dangerous. Thorium is another historically significant element with a long and productive story in human industry. It was discovered in 1828 by the Swedish chemist Jöns Jacob Berzelius. Thorium is weakly radioactive with a half-life of 14 billion years, making it persist for cosmological timescales. It was used extensively in gas mantles, which were mesh devices made from thorium oxide that hung in gas lamps, providing the main light source of many homes. When heated by the gas flame, the thorium mantle would glow brightly white with thermal light. Before electric lighting became widespread, thorium mantles were essential in providing bright light for homes, streets, and public spaces. Theatres, train stations, and wealthy homes used gas lamps with thorium mantles extensively throughout the late 1800s and early 1900s. Thorium has also been proposed as a future fuel for advanced nuclear reactors because terrestrial reserves of thorium are more abundant than uranium, and it can be converted into uranium-233 through neutron capture, which is then fissile. Some scientists and engineers advocate strongly for thorium reactors as potentially safer and more sustainable than traditional uranium reactors. Americium is a synthetic element that does not occur naturally on Earth in any significant amount. It was created exclusively in nuclear reactors and was artificially synthesized only because of deliberate human activities. Americium-241 is used widely in ionization chamber smoke detectors found in nearly every home and public building in developed countries. The americium emits alpha particles that ionize air molecules in the detector chamber, creating a small electrical current between two electrodes. When smoke particles enter the detector, they disrupt the ionization balance, causing a drop in current that triggers the alarm sound. Smoke detectors save thousands of lives every year by detecting fires in their early stages when escape is still possible. The radiation from the americium in a smoke detector is so minimal that the device poses negligible health risk despite containing a radioactive element. Most Americans have americium-241 in their homes without knowing it, working silently to protect against fire. Cobalt-60 was one of the most important medical isotopes of the 20th century and remains significant today in parts of the world. It was used extensively in gamma knife machines for precision brain surgery and in teletherapy units for external beam cancer treatment. Cobalt-60 emits strong gamma rays with a half-life of about 5.3 years. For many decades, it was the standard radiation source for cancer therapy, because the gamma rays were energetic enough to penetrate deeply into tissue and damage cancer cells, while the half-life was long enough that a cobalt-60 source remained useful for many years of clinical practice. Patients treated with cobalt-60 therapy often experienced excellent outcomes for various cancers, including breast cancer and cervical cancer. Modern linear accelerators that generate radiation electronically through Bremsstrahlung radiation have largely replaced cobalt-60 units in developed countries because they offer greater flexibility and no need for radioactive source replacement. However, cobalt-60 therapy machines are still in use in some parts of the developing world, particularly in countries with less developed infrastructure, because they are reliable, durable, and relatively simple to maintain without sophisticated electronics. Nuclear accidents have revealed both the tremendous energy stored in radioactive materials and the catastrophic consequences of losing control of that energy. The most famous nuclear disaster occurred at Chernobyl in 1986 in Soviet Ukraine. A reactor in the facility underwent a catastrophic meltdown when cooling systems failed during a safety test that went terribly wrong. The explosion destroyed the reactor building and released enormous quantities of radioactive material into the atmosphere. The radiation spread across Europe, contaminating thousands of square kilometers. Cesium-137 and strontium-90, both produced as fission products, were the primary contaminants, along with radioactive iodine that contaminated milk across the continent. These isotopes have half-lives of about 30 years, meaning they remained hazardous for decades after the release. Immediately after the accident, an exclusion zone was established around the reactor, covering about 1,000 square kilometers. Over 100,000 people were evacuated in the immediate aftermath, uprooted from their homes with little warning. Hundreds of reactor workers and firefighters died from acute radiation poisoning in the weeks and months after the accident. Many more developed cancer and other illnesses over subsequent decades. The long-term health effects from the radiation exposure continue to be studied and documented. Yet perhaps the most surprising and counterintuitive aspect of the Chernobyl disaster is that wildlife has begun to recover in the exclusion zone. The zone, though highly contaminated with radioactivity, has become a refuge for animals because the radioactivity, though dangerous to humans, is less immediately harmful to animals than the human activities that would otherwise occur in the region. Birds, mammals, and insects have repopulated the abandoned area. Some animals show measurable signs of radiation damage in genetic studies, but populations persist and reproduce. This demonstrates that even extremely high radiation levels, while devastating to human populations due to their short lifespans and complex biology, do not necessarily sterilize ecosystems permanently. The Fukushima disaster in 2011 occurred when a massive earthquake measuring 9.0 on the Richter scale and its resulting tsunami disabled the cooling systems of a nuclear power plant in Japan. 3 reactor cores partially melted. Radioactive material was released into the ocean and atmosphere, contaminating surrounding areas. The evacuation of over 100,000 people made Fukushima one of the largest forced relocations in modern times. The disaster revealed significant vulnerabilities in reactor safety systems and prompted worldwide reviews of nuclear plant design and backup safety systems. Unlike Chernobyl, Fukushima did not involve an explosion, destroying the reactor building, or a massive immediate release into the atmosphere. The spread of radiation was more gradual and in some ways more insidious, spreading through food chains and water sources. Radioactive iodine contaminated milk and crops initially, but decayed quickly with its 8-day half-life. Cesium-137 settled into soils and became incorporated into local agriculture long-term. The long-term cleanup is still ongoing decades after the disaster. Both Chernobyl and Fukushima have shaped public perception of nuclear power profoundly. Yet statistically, nuclear power remains one of the safest energy sources when measured by deaths per unit of electricity generated over the full life cycle. The risks are real and absolutely deserve respect and careful management. But the risks must be understood in context. The air pollution from fossil fuel combustion kills far more people each year, hundreds of thousands annually, than any nuclear accident could. However, the dramatic nature of nuclear accidents with their invisible radiation creates psychological impacts that persist long after the immediate crisis passes. Society's relationship with nuclear technology remains complicated, contested, and emotionally fraught. The future of nuclear medicine holds tremendous promise for revolutionary improvements in disease detection and treatment. New isotopes are being developed specifically for imaging and treating diseases with greater precision than ever before. Actinium-225 is being investigated for cancer immunotherapy because it emits alpha particles that can be precisely targeted to tumor cells while sparing surrounding healthy tissue almost completely. Lutetium-177 is being used to treat certain neuroendocrine tumors with remarkable success rates. These newer isotopes offer significant advantages in selectivity and therapeutic ratio compared to traditional radiation therapy, allowing higher doses to tumors with minimal collateral damage. Digital PET imaging systems with dramatically better sensitivity and resolution are being developed and deployed in leading medical centers worldwide. Artificial intelligence is being applied increasingly to interpret nuclear medicine images with greater accuracy than human interpretation alone. Machine learning algorithms trained on millions of images can detect subtle patterns that indicate disease before symptoms appear. The combination of better isotopes and better imaging technology and computational analysis promises to make nuclear medicine even more effective at detecting disease early and treating cancer while minimizing damage to healthy tissue. Theranostics is an emerging field that combines therapeutics and diagnostics in a novel way. The concept is to use the same radioactive compound for both imaging and treating disease in a cyclical, adapt-type process. A patient is initially injected with a labeled compound, and imaging is performed to determine if the compound concentrates in tumors. If the imaging is positive, showing significant tumor uptake, the same compound is then used at higher activity for therapy. If the imaging is negative, showing no tumor concentration, therapy is not given, sparing the patient unnecessary radiation. This approach ensures that only patients who will actually benefit from therapy receive the treatment, maximizing benefit while minimizing harm. The concept of precision medicine, tailoring treatment to individual patients based on genetic and biological characteristics specific to their disease, is increasingly incorporating nuclear medicine diagnostics. Biomarkers detected by nuclear imaging can guide treatment decisions rationally and prospectively. For example, a patient's tumor might be imaged to determine whether it overexpresses a particular receptor protein. If so, therapy targeting that specific receptor would be selected. If not, alternative therapies would be chosen. This personalized approach promises better outcomes and fewer side effects by matching treatments to the biology of each patient's disease. The challenge for nuclear medicine going forward is multifaceted. Ensuring adequate production and distribution of radiopharmaceuticals globally remains difficult, since many isotopes require cyclotron or reactor production. Training sufficient numbers of nuclear medicine physicians, technologists, and radiochemists requires long-term educational investment. Maintaining public confidence in the safety of nuclear technology, despite historical fears and real accidents, requires transparent communication and demonstrated safety records. At the deepest level, radioactivity is a stellar phenomenon. a cosmic process that connects us directly to the life cycles of stars. The radioactive elements found on Earth were created in the extreme environments of stellar cores or in the violent explosions of dying stars billions of years ago. Iron 56 is stable, the ultimate product of stellar nucleosynthesis, but all the heavier elements, including all radioactive elements, were created by processes that began and continue in stars. When a massive star with many times the mass of the Sun reaches the end of its life after burning through its fuel, its core collapses catastrophically in milliseconds. For a brief moment, the core becomes so unimaginably hot and dense that nuclear forces overcome all other forces. Nuclei are forced together with tremendous violence. Protons are pushed into nuclei, creating new heavy elements, creating the radioactive elements, creating the seeds of future civilizations. When the star explodes as a supernova, the most energetic event in the cosmos short of the Big Bang itself, these newly created elements are scattered throughout space. They become incorporated into vast gas clouds of nebulae that eventually condense under gravity into new stars and planetary systems. Our solar system formed from just such a cloud roughly 4.5 billion years ago. The radioactive elements in that primordial interstellar cloud, now spread throughout the Earth in rocks and soil and minerals, provide the geothermal energy that powers plate tectonics and keeps the Earth's interior hot and molten. Without radioactivity from uranium-238, uranium-235, thorium-232, and potassium-40 in the Earth's interior, the planet would be a geologically dead world with a cold, solid, unchanging crust and no volcanic activity. The heat from radioactive decay in the Earth's interior drives the motion of continents, creates the conditions for volcanic eruptions that shape the atmosphere, and generates the magnetic field that protects Earth from devastating solar radiation. Humans are therefore intimately and inescapably connected to stellar processes through the radioactive atoms in our own bodies and beneath our feet. The potassium-40 decaying in your cells right now, as you read these words, was created in a massive star that exploded before our solar system even formed. The calcium-40 that your bones are made of came from the potassium-40 that decayed over billions of years. You are quite literally made from stardust, transformed by radioactivity into the organic chemistry of life. Your existence depends on the radioactivity that powers the Earth's magnetic field and plate tectonics. Without stellar radioactivity, we would not exist. So when you sit in quiet darkness and consider the invisible forces shaping reality around you, remember that radioactivity is everywhere, unavoidable, eternal, and fundamentally tied to your existence. It has been part of our world since the very beginning, part of our bodies since life first emerged from the primordial oceans, part of the universe since the first stars began to shine billions of years ago. We have learned to detect it using clever devices like Geiger counters and cloud chambers. We have learned to harness it for healing and nuclear medicine, saving countless lives through diagnosis and treatment. We have learned to guard ourselves against its dangers through shielding and safety protocols. Yet radioactivity remains fundamentally mysterious in its quantum randomness at the most basic level. We cannot predict when any single atom will decay, cannot know which atom will be next. We can only calculate probability across vast populations of atoms. Science has revealed the mechanisms of decay, the mathematics, the particles, the processes. But the question of why radioactivity exists at all, why the universe is built such that unstable nuclei must shed energy and transform, why matter itself must evolve and change, remains one of the deepest mysteries of physics and philosophy. What we know with certainty is that without radioactivity, there would be no heavy elements, no chemistry as we understand it, no planets, no carbon and oxygen and nitrogen and sulfur, no life, no consciousness to contemplate these mysteries. The very fact that you exist depends on radioactivity. If you find yourself awake at night and thinking about the atomic world, about the particles flying through the darkness of your cells, about the invisible transformations happening constantly, remember that you are not afraid of something foreign or unnatural. You are contemplating one of the oldest and most fundamental forces in the universe, the process by which the cosmos itself reshapes matter and energy. You are touching something profound and real. Rest with that knowledge. Let it settle into your awareness. The invisible world continues its work, whether we are aware of it or not, whether we understand it or remain mystified. The atoms decay with the same steady patience that has persisted for billions of years. The universe breathes with radioactivity. And you, made from those atoms, breathe in and breathe out, living and moving and thinking, unaware of the nuclear transformations happening within you at every moment. The radioactivity in your bones continues its work. The potassium-40 continues to decay. The carbon-14 in your cells continues to transform. That is enough. That is the truth of radioactivity. That is the invisible music playing beneath all things, the deep rhythm of matter itself.